Good morning. So I think the survival phase of IK has started, so that you try to survive the evening and with some degree of dignity resurface in the morning. So let's seems to work. So thank you that you are here. This is the last session, and here today I want to not so much to give you even more examples of methods, but discuss a few fundamental issues that arise when cognitive scientists try to use dynamical systems to understand cognition. Okay, but first, a last glimpse on these notions that I finished with yesterday, bifurcations. Just to get you back on track. So we saw that in dynamical systems, special case continuous time, continuous value dynamical systems described by ODEs, by something like this. There is this phenomenon that if you play with those system equations by changing some parameters, here we change only a single parameter, but you could change more. You get, of course, different numerical behavior if you change parameters in the system equation. But importantly, if you change them typically a little bit, the qualitative behavior does not change. That is, if you had a stable oscillation and you change the parameters a little bit, a clock at the wall, and you change gravity constant a little bit, it will still be a clock at the wall and will be clocking, but a bit faster or a bit slower. So that's typical. You change control parameters or the equations a little bit, and what you get is just a little numerical change in what you observe. Systems that have this property, that are robust against qualitative change, are called structurally stable. But if you give them an overdose of parameter change, so if you keep on changing the parameter until you hit a critical value, then very suddenly the behavior of the system switches into a completely different performance type. For instance, on the left of this bifurcation, the system has just what is known as one stable fixed point. So regardless of how you started, you will see that the system evolves toward the final unique configuration. So a real-world system, what would be I want to include you into this. What would be a real-world example of a system that looks like this? So regardless how you started, it will evolve over time into one configuration or state that's always the same. So the most boring systems, how do they look like? Is someone able to give a concrete example? Yeah?
Top-down view on a funnel.
Top-down view on a funnel.
Yeah.
So, and if you look into it, you will always get dizzy and then fall into the middle of the funnel.
Yeah.
Yes, so that's a very psychological experiment. So, yes, that would be one example. Or, forgive me, a stupid joke. An IK evening always also unfolds according to this. So this is the point where you collapse into the bed. So that's the bed endpoint of an IK evening. So, and systems that would look like this, the system equation, they have a stable oscillation as the final determination, a single final oscillation, which is completely different than this in a certain sense. Okay, so much more should be said about bifurcations, and there are very many different types of bifurcations, which I will just not even start to investigate. If you're interested, there's a slide, and after the slide there's a pointer to literature. Okay, but I want to help you to prevent an error, a categorical error that I suffered from for, as I told you yesterday, 30 years. I did not understand the difference between phase transitions and bifurcations for the largest part of my life. So in physics, there is this notion of a phase transition. The classical phase transitions are connected with water. If you have a block of ice, you heat it. Then when the temperature of the ice goes above 0, it's water. So that is also something where you have a critical parameter value. In this case, it's temperature. Below 0, ice. Above 0, water. Directly at 0, hard to define. So if you ask physicists, many things can happen if you would be able to stabilize water at exactly 0. It's not possible, by the way. So this looks a bit like a bifurcation. And the physicists call such phenomena phase transitions. Okay, so it's the same thing from a very global view. You have a physical system whose behavior or appearance or qualities dramatically change and abruptly when a certain control parameter crosses a specific critical value. So that's the same in bifurcations and phase transitions. However, the definitions and the mathematical mechanisms behind this are very different. And now I want to briefly explain how the physicists look at phase transitions. So first of all, the background maths is different. Phase transitions are defined in statistical thermodynamics. So as statistical properties of systems like a bottle of gas that is made from very, very large numbers of interacting particles, so to speak. So the property of looking like ice or the property of looking like water is, in a sense, a collective state variable of a system of very many interacting micro components. Then, mathematically speaking, phase transitions are defined only in the limit when the population size goes to infinity. So there cannot mathematically be phase transitions defined for, let's say, 3 water molecules. Only if you have infinitely many, or at least so many that you can't realistically count them. And then there is actually, the physicists have a number of subtly different definitions for phase transitions, but they all basically have the same flavor. Namely, one looks at a thermodynamical global characteristic of such a collective system, the free energy, whatever that is, or it's a number that you can associate with statistical properties of such a system. If you change this control parameter, heat or temperature, whatever, the free energy also changes. And the classical definition of a phase transition is that if you change the free energy across, not the free energy, the control parameter across this critical value, the free energy undergoes a discontinuity. So either you have an abrupt jump in the free energy, that would, for instance, be when you freeze water, or the first or higher derivatives of the free energy go to infinity. And there are many different types of phase transitions. It's not only water and freezing. For instance, an important class of transitions are so-called percolation phenomena. When you have, let's say, a crystal, a semiconducting crystal. So I'm at this moment, in fact, personally involved with physicists who use these things to design new computational semiconducting devices. Then you may have heard of memristors. Some of you may have. So it's some people in the semiconductor industry place hopes in memristive devices for the future of neural network implementations on spiking super microchips, future blah blah. So super, but there is a phase transition needed to make them work. And the idea is that one has 2 electrodes, basically, between which there is an insulation material. And it is possible to, in a sense, heat very locally with very small energies ultimately this little system, and then little filaments or little super elementary wires of silver or other conducting material start to grow into this insulation material until at the critical value they start to meet or to grow to the other side, and then you have a short circuit, and that's what you want to have. And you can undo this again under certain conditions. So these are very sudden changes in the global behavior of a system when you have wires growing into a medium under certain statistical conditions with probability 1 they will meet, and you will have an overall shortcut. And if you, in a sense, decrease the probability of this wire growing, or the average length of these wires a little bit, the probability that they meet is 0. So you cannot have something in between. So this would be a very different type of phase transition, but it's a phase transition. So the world is full of phase transitions according to physicists, and it's full of bifurcations according to mathematicians. And the two things are mathematically very different, and also in the appearance. These are phase transitions are defined for, in a sense, static properties of systems, like being conductive or not, being water or ice, whereas bifurcations are for dynamical properties of a system, oscillating versus stable fixed point and so forth. Okay. There are mathematical cross connections between the two. If the statisticians model their systems with few global variables instead of doing the statistical modeling with very, very many micro variables, then one comes up with models that again look like PDEs or partial differential equations. And then you may have again bifurcations. So there are connections between bifurcations and phase transitions, but not on the surface. It's not the same thing. Okay, so just to prevent this misunderstanding that the two things are the same. Okay. Now, for the rest of this session today, I will be very much riding on the horse of attractors. The reason is, I will go into this in more detail, that attractors are one of the most natural ways to understand cognition in brains. So attractor dynamics and what happens with attractors, how you blah, blah, blah. So we will discuss this. So in a sense, understanding attractors is at least one important key to understand what can happen in very complex high-dimensional systems. And this in turn means it seems to be also important to understand what may happen in brains or in social systems or in whatever complex systems. At the end of the session, I want to confuse you again. So I'm looking forward to that. Okay, now, first of all, what is an attractor? You saw two examples, point attractors, that is, if a system has just one final state, which is always the end point of any temporal evolution. The classical model is not the IK funnel that you are pulled into at each evening, but just a bowl landscape where you have a ball and you place the ball somewhere in this ball, and it rolls down until it just reaches the bottom. Or a pendulum, a damped pendulum under gravity. You can start it as ever you wish. Under gravity and friction, it will end up just hanging down stably, period, but quietly, not doing anything. These would be fixed point attractors. Cyclic attractors you find whenever a system is doing an oscillation, a stable oscillation. So clocks that really do tick-tick, or a dripping water faucet, these are stable oscillation systems. These would be called periodic attractors. And then there are a few more. there are, I will briefly go back to this picture here. There are attractors and repellers. So attractors are, I'm now talking only about point attractors and point repellers. And a point attractor is a system state which is the natural end configuration of a system, to which it always sort of goes to rest. A repeller is in some sense similar. It is also a specific point that if you would start the system in this repeller in mathematical simulation, here the repeller is at the origin, then the system would remain at it. So the derivatives of the system are zero in this. It's called a fixed point of the system dynamics. You start it in a repeller. If it's a fixed point, it stays there, but it is unstable. If you kick it just a little bit, it will grow away from it. Whereas these are fixed points that are stable. So the classical diagram for this, I think you have seen this, at least I did in high school, with different names. It was called stable equilibrium in high school maths, unstable equilibrium, and neutral equilibrium. So if you have a bowl, not ball, but bowl, a bowl, gravity, and a ball, and a little bit of friction, then this ball will roll down and end up here. And if you kick it a little bit, it will jitter a little bit, but return to this position. That's a stable equilibrium, a fixed point. An unstable equilibrium, a repeller, is this situation, the inverted ball. If you place the ball exactly on top of it, it will remain there. But the slightest perturbation will make it go away. That's unstable. And then there are also neutrally stable systems where you place a ball on the plane and it can drift as ever it wishes. It's neutral. Okay, so one thing, why are attractors more interesting for understanding the world than repellers? Mathematically, if you would just invert time, attractors would become repellers and vice versa. So mathematically, in a sense, there's just a sign difference between the two. Just minus plus, so that's not a big deal for a mathematician. But in real life, why are we not interested as natural scientists in repellers? Yeah.
I think because repellers never actually occur, because you always have small perturbations in the
Yeah. They are just mathematical virtual constructs. You can't observe them because they always go away. If there would be one, it would, because it's unstable, the slightest bit of noise would make it evaporate. So they are, in a sense, mathematically there as boundaries between things that may happen, but they are unobservable. They are just not there, only for mathematicians. Attractors, however, are the things, basically everything that's there is an attractor. So a hydrogen molecule, or, well, basically everything that exists, that has shape, that regulates itself, must, so to exist as an entity, as an object, means you're in some way stable. You are very complex objects. Every one of us is a very complex object, and we have some degree of stability. So we do not immediately evaporate, disappear, or change shape. So there must be something that holds us together over time. Mathematically, this means we are in some way or the other, we are all attractors. Otherwise, we would not exist. And if I start thinking, then in my brain, I formulate thoughts, and hopefully, they also do not immediately dissolve and go away. I can memorize things, and I can think about objects or topics. I can concentrate on a topic. This means my thought dynamics must also be, let's say, have the property that it can attach itself to a topic that mathematically, it's clear, it's an attractor. So these are the first indications that the notion of an attractor is an important notion to understand reality, much more important than basically anything else we have in dynamical systems. In parentheses, later I will confuse you. I do not fully agree to this, but it is a common shared understanding that this is so. Okay, so going through the slides again. Now I want to give you a definition of attractors, because it's actually not so easy to define what is an attractor, generally speaking, because there are many different types. We saw fixed point and cyclic attractors, but there are more. There are so-called chaotic attractors, and maybe even more, and that's something that we will now see. So you're here, the doors are locked, the windows are closed, you can't escape. I will now briefly introduce you to a very abstract field of mathematics called topological dynamics. This is the most general way that I know in which one can define what happens in dynamical systems. It's far more general than ODEs or iterated maps or all of these things that we saw so far. It's what the mathematicians like. So the maximum degree of incomprehensibility for outsiders and maximum degree of clarity for the happy few who live inside this magic. Okay, so who of you has already been confronted with the notion of a topology, topological spaces? Okay, so it's more than half. Roughly speaking, so I cannot go into real math details here, but roughly speaking, the discipline of topology as a sub-discipline of mathematics tries to generalize as abstractly as possible from geometry. So what does it mean in abstract sets or spaces to be close to each other? We know this in metric spaces like our Euclidean space. We know what close means. But if you have spaces that are populated not by 3D points, but let's say by graphs, or spaces populated by words, what does it mean to be close? What is it possible to have something like distances defined? Or is it not possible? And if it's not possible, what else can we have? Questions like this are asked or are answered in the field of topology. A topology is basically, you could see, given some set, it becomes a topologically organized set if you define some kind of geometry on this set. And the only notion that we will be using from geometry is some idea of closeness. I will later use the notion of a neighborhood. That is one of the key concepts in topology. So in order to think geometrically in the context of some arbitrary weird set, topologists need to know what it means to be a neighborhood of a point. So if given any point in a topological space, it must be defined what other points live in a neighborhood. And for our purpose, it's enough to think of just 3D neighborhoods. So we know in our ordinary, Cartesian space, what it means to be close to each other and what is a neighborhood. But this can be done much more abstractly. Okay, so much for introduction to topology. Now, it turns out that the dynamical systems people try to explain everything. Okay, so this means they also want to explain phenomena that arise when time unfolds in weird spaces, not just in our physical 3D space that the standard physicists like, but also in spaces populated by ideas, spaces populated by neurons, spaces populated by signals, spaces populated I don't know what. So whenever there is some temporal dynamics acting on weird states, interesting things may happen, and there is an attempt in dynamical systems theory to have the most comprehensive unifying theory that is applicable always. And it turns out that this is, to a certain degree, possible. So to abstract away from those dynamical systems with ODEs, PDEs, iterated maps, all of the discrete models that we saw in the first session. There is a more comprehensive way that covers them all. It's called Topological Dynamics, and I will later introduce a little bit more about this. And it works always when the state space in which some dynamics evolves can be equipped with a topology. And basically, this can always be done. So, and in this very abstract view, it has been possible to define what is an attractor. So what makes, in a sense, stably observable phenomena arise in arbitrary dynamics? This is, I think it's very deep, that whenever one has temporal dynamics, something that changes over time, that hops between states continuously or discretely, whatever the states are, whether they are, whenever you have this, plus you have some idea of what it means for two states to be closer to each other than others, that is the notion of neighborhoods, then you, in a sense, universally and automatically get attractors. So, in a sense, it's unavoidable whenever you have time and a little bit of structure on your state space that you get notions of stability and also the opposite of instability and attractors. And that's, in a sense, the beauty of the field of topological dynamics, because it is so general that you might hope that you get very general insights into, well, what must happen in the world. Well, however God would do it, if whatever state space he invents, plus whatever dynamics he or she or it invents, if God has a mathematician at his, her, its side, ask the mathematician, and the mathematician say, you will have attractors, dear God. So there is no way to escape from them. Okay, and that's in a sense good, because attractors, as I said, are the things that make, that by definition are what is stability, that gives objects, that makes things nameable, because they persist over time. Okay. So that is my brief introduction into why it's interesting to think or speak about topological dynamics. So, and now comes a definition that is shared in mathematics of what is an attractor in a topological space. So, okay, so I will really just explain this slide. So if we have a topological space that is a set, call it X. And now this is defined for discrete time, so we have a map, iterated map that maps X on itself. So this means a map that just hops inside the space from point to point to point at time point, time point, time point, as we saw at the session 1, like a DFA. And this is a topological space. That is, we have an idea of neighborhood and closeness in this, defined on X. Then mathematicians say a particular subset of this state space is called an attractor if something happens. So I will go into these conditions in a minute. Attractors are subsets of state space. So if we have a point attractor, the subset contains just a single point. If we have a cyclic attractor, the subset contains all the points that you cyclically visit. And if you have chaotic attractors, it will be a fractal and so forth. So an attractor is a subset, and it is a set to which, intuitively speaking, all dynamics converge, at least if you're close enough to it when you start. So the mathematical conditions are an attractor set must be invariant under this transformation, which just means once you are in the attractor, in this subset A, and you apply a transition operation on it, you remain in it. So once you are in the attractor, you stay in the attractor. So that's condition number 1. And then second condition is, it basically says if you're close enough to it, you will be attracted towards it. There's no escape. That is the stability condition. So, and this is technically stated like there is a neighborhood B of A. So this is this yellow area around A, such that whenever you start your travel, your hopping sequence in this neighborhood B, called later the basin of attraction, then ultimately for any closer neighborhood, so we have actually two neighborhoods that we need to define attractors, the basin starting points plus something like little layers around, or neighborhood layers around attractor itself. It says then for any such green area that any boundary layer around the attractor, it happens that at some point when you start in this basin, you will be confined to a future that only lives into this yellow area, or the red one. You might also get attracted into A. So that's this technical definition. You do not have to copy this down or use it. The important thing that I want to highlight here is that mathematicians have found a universally applicable abstract way to define attractiveness. Once you have topological organization in a space, you can define attractors in this way.
But you still need to prove that an attractor exists if you have an
Yeah. This is just a definition. And then it turns out that, in a sense, under certain... then you do topological dynamics and you investigate under which conditions do they exist, how many are there, and things like that. So this does not say that in every system you have such a thing. Okay. So I want to show you now an example of attractors that are not of the typical kind that you find in textbooks, where you have these attractors with face portraits, as we saw yesterday. So this is a graphical representation of attractive phenomena in quite a different system, namely a finite cellular automaton. So the system that is, I will explain this step by step. The system that was investigated here is a dynamical system that has a finite state set, but a large state space. Basically, every point that you see in these graphics is one possible state of this. It's a finite state system, realized by a finite cellular automaton. It's not so important that we go into the details of how this system was defined. Important to know is it's a finite state space, so the state space X from the previous slide is just a finite set. And it had 2 to the power of 16 different states. And there was a deterministic map that just tells the system, if currently you're in that state, the next time step you will be in that state. So this deterministic map. And now you can just draw a large picture where you first plot all states. Every state in this picture is one point in your picture. And then you connect them by arrows, simply according to the transition law. So if point 1 goes to point 2 under this transition T, you draw an arrow between them. And now you draw all the arrows. And then you rearrange the points in your drawing plane that it looks nice. And that is what happened here. So all these points that you see here are some of these 2 to the power of 16 points, plus the arrows. They have been arranged that basically the arrows show from the outside to the inside. There were so many arrows that you don't see them. So you just see little points glued to each other, which means there are arrows which basically go from the outside to the inside. So that's basically the arrow direction. Here is a little blow up of one part of this large picture. And you see here these little squares are graphical representations of the states of the system. And then the arrows, actually they are not shown as arrows, just as lines here. You start here, next one is this, and then you end up here. And then you get into a cyclic path. So the transition operator just, well, propels you forward into a cyclic attractor. And so you see this whole system has a number of different attractors. There's one cyclic attractor where you end whenever you start in any of these green colored states. Then you're attracted or pulled towards this, and ultimately you will cycle here. Here's a little 5 periodic attractor in the middle of all of these states. This is, I don't know actually. So there are further cyclic attractors. And this here, what's that? It's one point that just loops back into itself. That's a very poor little lonely thing. It's a fixed point because once you start there, you remain there. But it has no real basin of attraction. It's a attractor without friends, so there is no neighborhood. It's a very isolated object. So you see, you can see things like attractors also in systems that you can't plot with nice face portraits. And this is generally true, in a sense, every kind of dynamical system that has a topology can be equipped with the notions of attractors. That is, with notions of stability, and if you wish, with notions of concepts or entities or objects that arise in the dynamics. Okay. So I will skip this. It's a classical textbook piece of a continuous attractor, but we saw this yesterday a little bit. So I apologize, I have to rush a little bit because other stuff is also interesting. Okay, so now I want to ride on one of my favorite private horses, namely think about the correlations or connections between symbols, symbolic reasoning, symbol dynamics, conceptual thinking in brains on the one hand side, and on the other side, what can the notion of attractor in dynamical systems give us to better understand rational reasoning, symbolic reasoning. Let me see what is the next slide. The riddle. Yeah, okay, a riddle. So, you have neurons, you are neurons. Or the neurons have you, I don't know. They just fire. So you know that. So if you could look into your head and if you could be your own electrode measuring every neuron, you would just be firing like mad all the time. So it's amazing that we don't have headache all the time. So that's what neurons do. When researchers look at your neurons, they see just spike trains. Altogether, you don't feel like that. You feel more like this. So you can close your eyes and you can start thinking. So scientists say that's your brain, you say that's I. Somehow the two must be the same. I think we agree on this, but it's interesting to think about it. How can this be the same thing? So the two are connected in some way, and there's a number of different traditions to think about this in philosophy, in cognitive science, neuroscience, mathematics. One term that has been advertised recently, the last 5 years or so, by a certain group of people, call it neural symbolic integration problem. But it's not the only way to call this problem. So the idea is there must be some very fundamental, the word again, between the rational high-level cognitive, conceptual, symbolic reasoning that we think we do, and this numerical, low-level, crazy firing stuff that the physiologists see if they start measuring you. Okay, so how can we approach this? There are a number of different ways of approaching this, but one of the most natural and promising ones, and also maybe the most frequently done one, is to try to identify concepts, words, symbols, well, the stable things that we can stabilize when we think, or that we can remember when we recall information. You have very stable things in your brain. So when I say house, then you all know the word, you all have certain memories attached to it, and you can all say the word yourself. So we all share, in a sense, one particular organization of brain dynamics that reveals itself whenever you say house, and you can address this attractor if it's an attractor. So, and you not only have this house token, attractor, symbol concept, but many, many others. So tens of thousands at least. So somehow we certainly in our brains have something that looks stable, repeatable, nameable, identifiable. So objects. Certainly our brain is a high-dimensional dynamical system. So now it's clear what is the next thing that I'm going to say. So it seems almost obvious that because in dynamical systems, the stable things, in a sense, by definition, are attractors, it's natural to use the mathematical model of attractors to understand how concepts, words, symbols, recollectible or addressable memory items can occur in brains. Okay, so this has been done in many ways and in quite different ways since about the 1980s, when it became fashionable to use dynamical systems theory to try to understand brains. So, and now I want to say some more words about this. So I will now pursue a little bit where do we get when we start from the idea that I will now just call them symbols that we have in our brain, or symbolic tokens, or there is not a real good word for this, that they should or could be explained by attractors. So I hope you feel this is fundamental. It is, I would say. And you will also later see, that's my second mission of the day, you will get confused. So you can look forward to fundamental confusion. So first of all, I want, yeah?
Sorry, just one question on side. Attractors is something that is stable, that stabilizes over time in a sense. The example you just gave, house or whatever, these are of course these are nameable concepts, but I wouldn't call them stable. Just when I try to address a concept of symbol in my mind, I wouldn't say it's a stable attractor in the dynamics of systems.
Yes.
How does that fit together?
It doesn't. It's you put your finger on one of the most critical and difficult points, and I want to spend at least 1 or 2 slides exactly trying to not to answer but to address this problem. It's a critical problem. Okay, but first of all, I want to say there are other models that have been abstract mathematical models that have been proposed to account for symbols in brains. So, for instance, if the trajectory of thinking passes through certain regions in state space, you could say this region is the symbol. There's nothing like stability or attractivity. It's just, if your brain state looks like this, you are thinking currently of a house. then you might say, okay, even simpler than that, it's a special case of this here. When certain neurons fire and are active, I'm thinking of a house. That's local coding, or space coding, or grandmother cell, or whatever coding. This is, by the way, not incompatible with attractor models, because it might be that if certain neurons fire, they are stabilized in their firing patterns in some way. Another thing which is mathematically quite intriguing is that you define dimensional directions in state space with concepts. That is quite abstract. It's neither locations nor attractivity. It's something like basic coordinates of thinking are concepts. But then you end up in mathematical trouble how to stabilize these things. Recently, well, not so recently now, 10 years old proposal that is discussed back and forth in the theoretical mathematical cognitive neurosciences is so-called saddle node or homoclinic cyclic dynamics. I just mentioned it. I don't have time to go into this. It's a compromise model of you could say partial attractivity and partial repellivity. Conceptors, that's a model that I added to the soup myself. So, and again, I will not spend any time explaining this. I just want to mention attractors are not the only candidate for mathematical representation of concepts in neural dynamics. Yeah?
I just think, doesn't this already exist with the individual neurons, like the Jennifer-Anderson neuron or the Star Wars neuron? They're neurons that only fire for a specific concept. Could be a picture, a word, could be a sound, everything that's related, for instance, to Star Wars. And then this specific neuron fires. Yeah,
if that would be... so I'm not a really good neuroscientist, but my feeling is... my feeling is that it's debatable of whether these things exist. So I don't know who is the most knowledgeable neuroscientist here. What is the current state of discussion on whether local individual neuron coding of concept is there or not? Does anyone have the latest news?
I've seen a talk by a person who did this.
Yeah.
Electrodes in the brain and then single neuron.
Yeah, this can be done, but the question is how repeatable is this? So as far as I recollect from similar discussions since Hubel and Wiesel discovered these receptive field neurons for specific visual gratings, that seemed a solid story in the beginning, and now it's not solid anymore. So when you start looking critically at these experiments, you might find that under different experimental conditions, the same neuron would also fire under different conceptual input.
Yeah.
Yeah. So and then you have it. Then it's not clear how the coding is done, because you might also have other neurons that you did not happen to record from in this experiment that would also fire, at least in the context of this experiment when this particular concept was presented.
Yeah, of course, I think that's the case, yeah.
Yeah, that seems, but this makes the whole picture of local coding very diffusing. It's not a very clear picture. And stability conditions, so how this can be repeated, let's say in 3 years from now, given the plasticity of the brain, will the same neurons still fire under the same conditions or not? These experiments are not made for good reasons, and because it's just practically not feasible. So I'm not a neurophysiologist, so maybe there are better experiments now, but my take-home message was always that there are indications of local coding, but how exactly that works is unclear, and how stable it is, and how adaptive, how strongly it can be modulated by context information. That would be my feeling, but I don't know the latest news from that field. And even if this is so, it's unclear whether this would be a case of regional coding or of attractor coding, and you could mix the two even, depending on whether there are additional stabilization mechanisms for this or not. Okay, so this slide is just there to tell you people think about this and they come up with a number of different mathematical approaches to try to pin down what could be concepts or symbols. Okay, so now we come to this critique. Symbols as attractors, it's an inviting idea because of the stability thing, because we can recall and we can concentrate, that is, we can mentally explicitly stabilize a concept in our brain. By the way, if you try to stabilize the concept of house or the word, is that a periodic or fixed point attractor? So if you try to think of house for a few seconds and really think of the word house, then probably you repeat it in your mind. House, house, house. You cannot. So it seems more like a cyclic attractor, if at all, than a point attractor. Interesting questions. Okay, so that is one reason is that there is something like stability about concepts. It's built into the notion of a symbol that it is recognizable, that it is stable over time, that you can put down a symbol on the table and later do other things, come back home, see the symbol there and use it again. So that's the nature of a symbol, that it's a token that's stable and addressable, so to speak. And we have something like this in our brains. So very natural to think of this temporal stability thing as attraction dynamics. Furthermore, one of the most famous, if not maybe the most famous model of abstract computation in neuroscience, the so-called Hopfield network model of memory, uses fixed point attractors to encode concepts. So it has been done by our forefathers in neuroscience already. So it's a very classical idea. So and then there's this big contra-argument, namely, when we think, we are not ultimately captured by a concept. If I think of a house, next moment I can think of a garden, next moment I can think of a flower, and so forth. If it would be really an attractor house, then I could think of house only once in my life, and then I would be stuck with it. So apparently we can jump out of these attractors, if attractors they are. Yeah?
So you mentioned that this is a topological space, and then these attractors exist due to this topology. And can we think about some other component of the system that basically changes the topology, and then the attractor that was an attractor a moment later is no longer an attractor?
Yes.
Okay.
Yes, that is. So that's one of the possible answers given by physicists and mathematicians to this fundamental problem that you want to have stability, attractivity for concepts, but you also need a mechanism to leave this attractor again, because thinking means you transit from idea to idea to idea, from attractor to attractor to attractor. Mathematics tell you this can't be. An attractor is nothing you can leave. So by definition. So yeah?
So I was thinking at the moment where you're talking about house that you think of it like intermittently. Like, could it be that it's rather like a repulsor, that you're just putting energy to bring it into this point where house, and then it's repulsing, and then you put energy to put it again back into its place, and then it's like in the ball there is up there the house in this mountain, and then it goes away, and then you put energy to bring it back to house.
That is interesting, a very energetic way to look at thinking. Yeah. So. This is certainly a model that I have not read about yet, but it looks dynamic, so it looks nice. Maybe we could talk about it the question is after or before a beer. So
Depends on how much creative you want.
yeah. So I will briefly outline a few ideas. One of them is the one that you mentioned, that have been proposed in theoretical neuroscience to explain this dual nature of attractivity, stability, versus transitions going from one concept to the next. So a brutal approach that is to just say the brain is noisy. So if I'm thinking of a house, then also I have so much neural noise that this will sometimes kick me out of the basin of attraction again. So this is, I think, why is that? So I don't think this is a good explanation. Why? I mean, it works. So if the noise is strong enough, you just are kicked out of the basin of attraction, and you end up in a new basin of attraction, of the next concept that you think of, yeah?
It doesn't give you a way to organize.
Right, it's too random. So I hope that we are not just noise-driven thinkers, but also we have some way to have very organized ways of thinking. So that's not really nicely explainable by noise. Then there's this idea that the brain undergoes bifurcations all the time. So that in some way there are control parameters, actually very many in your brain, that are changing at let's say at the time scale of seconds, and they make attractors appear and disappear. As we have seen in this bifurcation diagram, it's the nature of bifurcations to create new attractors or destroy existing attractors. So that would be a nice thing. So there are attractors, but only for limited time. And then the control parameters of your brain change. And then the attractor is gone and no problem to be ultimately captured by it. So this has been explored in many ways, this basic idea. There are even fancy names for this. For instance, the name of an attractor ruin. That is what is left over after the attractor has disappeared due to a bifurcation. So what is, there is one nasty fact about this way of thinking or of modeling that makes it not so easy. So what would you think is problematic about this view? Yeah?
I mean, basically moved everything to the meter level.
Yeah.
Interesting.
Yeah. In a sense, you just have said it's someone else's problem, but this someone else will have the same problem. So where do the control parameter dynamics come from? So the control parameters that dissolve and create attractors, they also must be generated in your brain. So then you have a control parameter dynamics, but then you have the same problems. So it is basically, you are led to the idea of having hierarchical levels of thinking, where higher levels of thinking control lower levels of thinking, but this leads to other problems, because where does this hierarchy end? And does it end? And also, do you think at many time scales? So do you have slow, so you would need different time scales. Higher levels would be slower inherently. And is that true? So it's not easy to come to a conclusive or elegant picture in this way.
If these are recurrent, like higher levels affecting lower levels and lower levels affecting back higher levels, so would it solve this problem of infinite hierarchy?
No, then you would lose the so the mathematical concept of a control parameter is that it must be changing. If it's normally it would not change at all. So the picture that I showed yesterday, this control parameter A was a constant. It did not change at all. So you fix it and then you see what is happening in the system. This still is to a certain degree a good approach if the control parameter is allowed to change slowly, but it must change slower by enough orders of magnitude to allow the system to sort of develop its relatively fast dynamics in order to show that it is in attractors and so forth. So it is necessary for the notion of a control parameter to be slower or essentially zero speed than the dynamics it regulates. So you cannot have this nice idea of having sort of control parameters are regulated by a system that's as fast as the system that is controlled by the control parameter. That doesn't work. Then it's not a control parameter anymore mathematically.
Yeah, but if the timescales are different, but the higher level kind of integrates stuff over time, and there is a bifurcation in the higher level which leads to bifurcations in lower level, would it be possible?
Yes, it would be possible. And it's a common idea to structure artificial intelligence systems based on neural networks. But it does not explain where at the highest level the bifurcations, the attractors come or go away. So it's yeah.
Just from the biological side or the neuroscience, I think it's in particular interesting for neuromodulation, for example, because you have different time scales, either by how long the molecules exist, and also how far they can diffuse. So you wouldn't have like only synaptic transmission, you could have also several different combinations of transmission on different sides, together with different parts, and so this could bring you different time scales.
Yeah. When one starts thinking about it, one sees a universe of possibilities. And so it's not...
But they exist.
Yeah. So another... so mathematicians have been confronted with this problem and they have suggested a number of different escapes. Another one is called unstable attractors. That is, seems to be a contradiction in terms because an attractor by definition is stable. However, there are in higher dimensions I would say weird phenomena where you have attractive dynamics that are attractive only in certain manifold. So forgive me in talking to you in riddles. But these unstable attractors, they are both attractors in that they they look like attractors, they feel and smell like attractors, so they are attractors, but while they are attracting their system trajectories to the final attracting set A, they also lead it into an area where it becomes a repeller. But this means then in an orthogonal direction in terms of manifolds. So you have transits between different manifolds. And transits between different subdimensions. It's a very delicate thing. It has been worked out at the Max Planck Institute for Dynamics, blah, 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 in where was it? In Göttingen. There is one. And I heard the talk of this mathematician, and it seemed like a contradiction in terms, but they even proved that under certain conditions, especially in spiking dynamics, that's interesting. So then this is a generic phenomenon. So it will always happen, these kind of unstable attractors. So again, we cannot, in this context here, go any deeper here. All I want to say is that there are a number of sometimes mathematically quite refined and subtle and strange efforts to reconcile the idea of attractors to explain symbols with the necessary flexibility to leave them again, to have, let's say, transitions between attractors. My own, so now I'm getting, let's say, I will also insert a little bit of my personal opinion. My personal opinion is that we currently simply do not know how to do this right as mathematicians. These are high-dimensional systems. So this is now opinion, not reporting, but my personal opinion, is that in very high-dimensional systems, such strange things can happen that we have no idea to even describe in the first place. Our metaphors of attractors, repellers, bifurcations come from low-dimensional systems. And in high-dimensional systems, you have so many more degrees of freedoms of things that may happen, and we still lack the maths to do this. That's my personal conviction. So I try to sell my services as a mathematician. You see, so we need more people that are mathematicians, so fund them. Okay, so now the final chapter. I want to alert you to a weird little thing, namely that brains have input. I talk to you, you have sensors, you listen, you smell, you see. That makes your brain a non-autonomous system. And now I want to explore a little bit the fundamental, again, consequences of this fact. That brains are non-autonomous. Yeah, so actually what is, if I summarize the last 40 years in cognitive neuroscience, then there was a trend that started in the 1980s to use dynamical systems concepts to understand cognitive dynamics or neural dynamics. This is historically not obvious that this happened, because before that time it was basically symbolic logic and the classical AI traditions that were used to model cognition. But then there was this change in perspective, or this additional perspective of using dynamical systems theory. This coincided with spectacular developments in physics and mathematics, the discovery of chaos, the ability to plot fractals and have beautiful graphics. So there was, in a sense, a general appreciation in the wider public that dynamics is super, chaos is brilliant, fractals look beautiful, everything is ruled by the butterfly effect. So the world is a very romantic place of wonderful, colorful dynamics. I think something like this happened. So it was very fashionable, very elegant, very beautiful, and to just talk in terms of dynamical systems. It was in the air. However, so there's one big, I would say, fundamental mistake that was made, unknowingly. So people were just not aware of this mistake. The tools and concepts that were imported from physics and dynamical systems theory all came from autonomous systems. So the notions of bifurcations, attractors, all of these things that have been used so many times to describe what's happening in the brain, they are all defined by mathematicians for autonomous dynamical systems that have no input. And if one reads papers that claim that there are attractive phenomena, that there are certain Lyapunov exponents, that are blah, 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 so chaos, whatever you name it, I find this as a mathematician in a paper written by non-mathematicians, physicists often. So there is all of this cultural thing between physicists and mathematicians. And then they say, okay, so we have numerically quantified this attractor state in this neural dynamics in this slice with the Lyapunov exponent of blah, blah, blah. And then those poor people do not understand that everything they wrote makes no sense whatsoever at all. Because they are using a concept of attractor and the tools to measure degrees of attractiveness that have been defined for autonomous systems. And now I want to take you on a little journey, a very bumpy journey, into the mathematics of non-autonomous systems, systems that are input-driven. And brain systems are input-driven. I think that's basically the nature of information processing systems, that there is input, namely the information that's processed. And then it turns out that the maths of dynamical systems for input-driven systems is widely different from the math that has been formulated for autonomous systems. And the math is not only different, it's also much more complicated. And it has been addressed by mathematicians only since about 15 years or so. It's a very young discipline within pure maths to look systematically at what can happen in input-driven systems and to try to transport the intuitions and ideas from autonomous dynamics, like attractors and bifurcations, into input-driven systems, non-autonomous systems. It's a very small community that does this. So I would say about 10 mathematicians worldwide are really doing this at a high level. It's not an established field. I'm not doing this myself, and I lack the math background. But I had in a sense, the luck and the privilege that for some years in my group there was a mathematician by the name of Manjunath Gandhi who worked exactly in this field, in non-autonomous abstract mathematical modeling in topological dynamics. And what I learned from him is what I'm now going to show you in a few slides. Namely, a first glimpse into notions of attractiveness in non-autonomous systems. And you will see it looks different. And my claim is that is the only appropriate way to handle attractiveness in brain-like systems. Not the stuff that we have been doing for 40 years. It's fundamentally misguided. Okay. So that's my personal opinion. Fine. Now you heard this. So, a little bit of formalism. Non-autonomous system is basically just, it looks like this. In the discrete time case, xn plus 1 is a function of x previous, but the function itself changes with time. So this change of time of this operator can come, for instance, from input. For instance, if we define Tn at time n, the transformation of x of n is some transformation operator that does not depend on time, but we have a temporal input that modifies this basically. So this is a special case of non-autonomous dynamics. Other cases are when you look at random systems. The stochastic time series, mathematically speaking, are also non-autonomous systems. What is known as the noise term by physicists, that's basically an input term which makes this transition function non-autonomous, yes. So that is the, as soon as you have input or perturbations, or you have learning, so if you have intrinsically time-varying operators, you're dealing with a non-autonomous system. Okay, so we will have this Tn of x of n thing here. Yeah, so I will give you, just in order to make this a little bit less abstract, an example of a non-autonomous system. Yeah?
Sorry, one more minor question.
Yeah.
For some time. Usually, or quite often, when people talk about input-driven signals, they add this time, subtitle for time, and then they say, okay, changes with time, and that's fine. But what about causal relations to what the system is actually doing? So because what happens at time point n might depend on the input at time n, might depend on the state of the system at time n-1, which is something that is different in different spaces.
So you want to have, like in analytical modeling spirit, you want to dissect this T operator into sub-mechanisms that feed in input versus something that...
I'm missing the input, say, the current state of the system in the definition of T.
This is the current state of the system, and if you have it, I never thought of this as problematic. you want to have.
So I think you want to have u depend on x n minus 1.
Is that true? So you want the in. So
basically modeling external dynamics using an external mechanism. I mean, if you plug in a system in native physics, then the system itself has an intelligent behavior, which you might want to capture that too. But you also have an external dynamics.
Now I get it, yes. So this is in fact an escape that has been taken by some very theoretical people, like for instance Friston, to solve this problem of non-autonomous dynamics. They say, okay, we have input, but the input comes from an environment, and the agent plus the environment, we can put an enclosure around it, and then there's no input to this system. So there are just two subsystems that interact, the agent and the environment. And what is input to the agent is sensor input. You have feedback from through actions from the agent to the environment, but altogether it's a closed system. And then if you describe the total system, environment plus agent, you have an autonomous system again. That's mathematically fine, but it doesn't really help you to understand brain dynamics. So, so that's one possible mathematically clean escape. But it's, I can only repeat myself. It doesn't really help you to understand brain dynamics. Friston would punch me for this. So, okay. So just a little example of a non-autonomous dynamical system that was trained by a master student, Razvan Pascanu. Some of you may know him because he gave a course here last year. This is a system, a neural network system, that was trained on a task to predict the next symbol in an incoming, let's say, video stream of coarsely printed symbols. There were bracket symbols like this or this, and normal letter symbols. And the text statistics of the text that was passed to this network was actually hierarchically structured. There were 6 nesting levels shown by the brackets. So when a bracket opened in this incoming stream, the following text of non-bracket symbols came from a particular grammar. If the next bracket level opened, the system, the text was generated by another grammar. So there were 6 grammars which were switched in between by switching between by inserting these bracket symbols. And the network had to learn to predict the next symbol. In order to understand the next symbol or to predict it, it would have to know which is the current bracketing level, because then it would use a different grammar to predict the next symbol. So the system basically had to learn this, and it did so. So it was successfully trained. And the interesting or important thing for our discussion is that this neural network had a sub-module, so to speak, that did this context switching. So there were, for each nesting level, there was one neuron that, when it was switched on, indicated to this network that now you are in this particular nesting level, and you should process incoming symbols according to this particular grammar. Fine. So all I want to highlight at this point is not the machine learning aspects behind this, but the fact that here we had a system which could switch between, you could say, different conceptual processing states. Namely, now the system thinks I'm in switching level 2, and now I will consider incoming inputs according to these laws. Then it could switch to another nesting level if another bracket would appear in the input. So for all, I would say, practical or intuitive purposes, this system could switch between different attractor states. So this switching was stable. And it was stable because these neurons had strong stabilizing feedback loops. So these neurons really could lock into 0 or 1 states, and in this way give guiding information to the entire system. So it seems obvious that this system could switch between different attracting states. However, in each of these attracting states, the system was processing input. So if you would plot the system dynamics, you would not see anything like a nice cyclic attractor or anything. You would see just very crazy system dynamics, as you would expect from an information processing neural network. And this leads to a mathematical modeling challenge. How do I properly describe what's happening in this network? And the answer is not clear up to now. So there was a paper at that time by Wolfgang Maas and Eduardo Sontag. Maybe Eduardo Sontag is known to some of you. Who knows Eduardo Sontag? None. Good. So Eduardo Sontag is one of the, I would say, the most powerful, celebrated, and famous modelers in nonlinear signal processing. So he has written the standard super heavy textbook reference on nonlinear signal processing. And he teamed up with the spiking neural network person, Wolfgang Maas, in order to understand basically this here. So there's a paper written by them where they try to come up with a mathematical model of a spiking neural network switching between different processing modes in a stable way. And my feeling is that even Eduardo Sontag didn't do it right in that paper. So, and I have no better approach. And on the following slides, I want to at least give you some numerical insights into what might be happening in these systems. So I have 3 more minutes. Now, I skip these parts. First thing that I want to show is that, or highlight, is that once one has input-driven dynamics, the notion of an attractor becomes unclear. Mathematicians have proposed a number of different concepts for attractivity, attracting sets, that are not equivalent, and there's no agreement on what is the right way of doing it. Here are the 2 most frequently used concepts are so-called pullback and forward attractors. So this is time from left to right. We are now looking at an attractor is now a time-dependent set. That's one thing that is different in non-autonomous system. It's not a fixed set, it's a time-dependent set. So the attractor may move. So here, across time, the attracting set moves forward. And if you define it by pullback attraction, then this means that there must exist, you could say, a basin of attraction around it, such that whenever you start in the past, the further you start in the past, the closer at current reference point time you will come to the attracting set. That's called a pullback attractor. It's a definition of what attractivity might mean. And you could also look into the future and say, okay, I have this sets of A's, A1 to A, these would be called an attracting set, a time-dependent attracting set. If whenever I start in an environment at any time, ultimately any trajectory that starts here would be pulled towards this attracting set in the future. These 2 definitions are equally plausible, but they are not equivalent, so they are even orthogonal. You can have one and not the other, and each of them. And some attractors have both properties. They are then called uniform attractors. Okay, so I would just point out that the very notion of attractivity is unclear, not at least as immediately clear and uniformly accepted as it is in...
Is it needed?
Needed?
Yeah.
Yeah, that's one. And to have a notion of attractor is one of the first things that one wants to have in dynamical systems theory. It is the big organizing principle. So without it, they feel not satisfied.
As you said, yeah, exactly.
it just may be a feeling they have because of this tradition you mentioned.
Yeah, maybe it's they are on the wrong track, but at least they try, and yeah, maybe that's
by itself stabilizes the system.
Yes.
And
but then you have a notion of stabilization that comes from signal processing, that has not very much to do with this here.
But do you need, again, what if you found this sort of appropriate concept of an attractor for this kind of system? What would you have gained?
I don't know. So here I'm reporting what people are struggling with, and there's a historical reason for this, and there seems to be a conceptual foundation for thinking about attractors, but you might be right that it is that it's just the wrong track, that we might find a completely different mathematical, conceptual entry point into understanding non-dynamical systems, but I don't know it, so I can't offer it to you, but it might be, yeah. So I still have 30 seconds. So my take-home message, so how many more slides do I have? There will be a leftover thing that you can only then see if you download the slides. But the basic message is that my feeling is that we are far from having the final mathematical answer and the final mathematical tools to understand to actually describe what is happening in brain-like systems. We see it when we start to look closer at concepts like attractors and non-autonomous dynamics, then we are forced to admit mathematicians don't give us at this moment the right tools. Which means that for the end user of maths, this is frustrating news, because you might feel you just will not have the right tools to do what you want to do by way of modeling. So you will always be, how do you say, procrastinated or pressed into schemata of thinking that are too narrow and inadequate. They are imported from 300 years of physics. They are imported from a little bit of signal processing, but the brain is different, but you can only use what's there. So that's bad for the end user. And maybe you should just forget all of what I'm saying. It's safer. But for mathematicians, that is wonderful. Because this means you can unfold, there are plenty of unexplored terrains in dynamical systems theory that just are waiting for you if you happen to. Who is a mathematician? Nobody here. Who would want to do something like that? One, yeah. You have to, because he's my PhD student, so. Yeah. Okay, so I'm now approaching an age where I feel time is running out from me, that I will not live long enough to see this. But you might still be among the happy ones that someone in your generation will find new breakthroughs. I think there are breakthroughs to be done and found. They should be possible. I have no idea how they will look like. I would be very curious to see them. So with this note, I finish my presentation. There would be a few more slides, but coffee time is also very important. So I wish you a nice rest of IK and see you next tonight.